Welcome back after fall break. I hope you had a good time. How many of you went home? A few. I guess probably the ones where home was closer than others. Yeah. A couple of things. So you have your exams back. The solution to the midterm is posted, so you can take a look through that. Let me see if there's anything I wanted to mention specifically. Yeah, so one thing I wanted to mention, so more than half of you got this right, but nonetheless, this is an important point. So number one, given the gradient just calculated, will weight 3's value be increased or decrease in order to reduce the loss? And it's depended on what you got for your weight gradient in the previous portion. So it should have been negative, but if you said positive, I just went with whatever you had. But since the gradient was negative, that means that if we look at the slope, right, we must be something like this, right, because we have a negative slope. So therefore, if we're trying to get to the minimum, we need to go to the right, which means we're increasing x, right? That's one way to think about it. So that's sort of the pictorial way. The other way to think about it is that we subtract learning rate times gradient from our weights. So that's a more direct algebraic way. Let's see, for number 7, which was the five-layer neural network. Yeah, Principal.
It's possible that we could have been coming from the right of the graph.
So here's, let's see. What we know is currently our weight is here, right? That's our value for our weight because we're evaluating our slope here. Now go on with your question.
My question was if we were on the right side of the graph, I guess our slope would be positive.
Yeah, so if we were on the right side of the graph, like let's say here, then our slope is positive, and we want to go to the left, so we'll be subtracting the weight. Okay. So for number 7, basically I just figured this would give a good way of ensuring that you really understand how these convolutional neural networks are organized. And most people did fairly well on that, but any problems you have on here, make sure that you understand what went wrong. And if you need to come talk to me, feel free to come talk to me. I didn't say anything about making it a useful neural network, okay? And so there were no points taken off. But having like 3 layers of max pooling in a row, is that, for a moment I thought, wait, that's just equivalent to a single max pool. Is it? Why not? Let's say you did something simple, where you were just doing stride equal your max pool size, right? So we were taking, let's say, from 100 by 100 down to 50 by 50 down to 25 by 25. And so my question is 3 max pools in a row the same as 1 max pool? Assuming that latter max pool, you could set up the stride so it would be the same exact cells. You think it's the same? So here's the key thing is, if we have our the activation function, right? If we have an activation function at each level, we're actually doing some difference as we go along, but it's kind of minor. So I preferred having a mixture of max pools and convolutionals, not having max pools in a row. For number 8, I was extremely happy that basically everyone got the idea in the bird identification model is what could give us lower accuracy in production. Any questions? Like specific questions about yours, come and see me afterwards. The other thing that I wanted to follow up on is the midterm evaluation that we did last Monday. So just a couple things I wanted to go over. About 5 people said it was too fast, 2 said it was too slow, and the rest said it was just right, although 1 said it with high variance. So I think that, in combination with another comment I'll mention in a moment, means I should slow it down just a hair, okay? So, and that other comment was more rigor in the math. So 1 or 2 people had that. So, or to go more slowly during the math. So I think that's probably where I'll hit with that. Both more rigor, more carefully going through it, and slightly slower going through it. People like the slides, videos, and notes posted online. A few people mentioned the homework in particular, and someone liked the coding homework. Office hours, I don't think it was the hours themselves, but they're coming and liking them. So, the 2 biggest things people didn't like were errors on the slides, and I understand, and shouldn't have that, and I'm sorry about that. So there, I'm sure will still be some errors that creep through, but here's what I will do for sure, is I will correct the slides and repost them so that what is posted on the slides is absolutely accurate. Okay? And I will do my best. The other was missing a big picture. So I need to, we'll talk a little bit about that today, and I'll try to make sure that we are grounding sort of where we are in the big picture of neural networks and deep learning. There was a request for consolidating resources, that there was no one single collective site where everything is. So here's what I did. Piazza is now the one place where everything either is or points from. Okay, so there are still things in Google Docs, there are still GitHub and so on, but let's go ahead and just take a look at that. And if I'm missing any resources, please let me know. So basically the resources has everything, like, here's the midterm solution, our main GitHub repository, every one of our assignments, a link to the course gradebook, the videos, the slides, the notes. So if I'm missing anything, please let me know, and I'll be happy to add it there so that you have one place, because I can understand that's a problem. Someone thought it'd be really cool if we had a student tutor, like a Gruder. And I thought, wow, we have one. So I haven't been very good at communicating. So Matthew took this class last year, and he's got these 3 hours of office hours. All right. Has anyone talked to him? Excellent. Okay. Class exercises would be helpful, someone mentioned. It so happens we're doing one today. A schedule for the rest of the semester is somewhat more filled out. So we will be talking after today, about recurrent neural networks, which are really what's used mostly for text analysis. It's used for text. It's used for other things like speech to text and so on. And that'll take us some time to go through. It's as rich as convolutional neural networks, although I'd say slightly less far along. We're going to talk about reinforcement learning. We have a couple TBDs. We do have, somehow I lost and I will have to put back in, we have a guest lecturer, a grad student from Northern California, who's going to come down and spend probably half a class talking about his current research in neural nets. There was a request for more office hours, so I did go ahead and add some more office hours. So I added before class on Monday, and then I also added an additional 1.5 hours Wednesday afternoon. Okay. If those don't work for you, I'm happy to try and meet by appointment, but it'll almost always be Monday or Wednesdays, because I live out in Redlands and I'm not normally here the other days of the week. Okay. Abo.
Just out of curiosity, on the schedule, it says we'll be covering generative adversarial networks.
Yes.
How deep will we go into?
Well, if it's just one, if we end up with just one course, one class, then not terribly deep. Are you particularly interested in them?
Yeah.
Okay. Does anyone else even know what they are? All right. So they're Maybe what we'll do is move that a little bit earlier, and then if there is great interest, we can maybe have more of that. Okay, the other thing that I did, so I have not been happy with my tablet. So I know my writing looks really bad. It's not that bad, okay? And so I was looking over the break at getting a Surface, because those like seem to work. But I had to kind of check that out quite a bit because, you know, it's $1,500 or something like that for a nice one. So I looked and then figured, well, what software would I use on the Surface? And Microsoft's OneNote seemed to make sense. And then I checked, and wait a second, there is OneNote for Mac that supports styluses, tablets. So we're trying that. My initial experiments with it makes it look pretty good, okay? There are several things I like about it, but there's going to be a little bit of a learning curve to get used to that. And part of what we're giving up is build slides where, you know, they have animations in them. I don't know how to do those and still use OneNote. So if there's a really important animation, I'll just have that stand alone without me writing on it. Any questions? Okay, so OneNote. Even this, I think, looks better than what we had before. To my mind, it certainly it feels like what I'm drawing is what I am intending to, what I think I'm drawing, as opposed to it doing some other weirdness. So we left off last Monday with object detection, and I want to do a quick review of that and then go over that in more detail. So our goal was, what we already knew how to do was image classification, right? You give a picture that should have one object in it or one object that it knows how to classify, and it will give you back classification, which includes a probability. So, and really we get even more information than this, right? What other information do we get besides dog is 99.3%? Evan? We don't now get a box. Later on, we'll work on that. So right now, just if we talk about the classification problem, what other information do we get? Yeah, we basically get 0.07 information about all the other things that it's pretty sure it's, you know, that it's not. So you get probabilities not just for what it thinks it is, but also for everything that it's less convinced it is. So what our goal is object detection, right? To provide for multiple objects in a scene, in a picture, not only what it is, but also a bounding box around it. And we looked at, well, first off, in order to do this, we have to have ground truth. So we have to have some training examples that have both a bounding box and a category. And Pascal was such a data set. And then we said, well, let's simplify our problem, right? Let's first just say we want a bounding box and a category, so a classification. How can we do that? And the key here, and this is not just for the object detection problem, these three questions. These three questions are really questions you want to ask yourself about any deep learning problem you're trying to attack. What's the data, including, of course, labels? What's the architecture? That is, what does the neural net look like, including what are the outputs? And what's the loss function? Okay. So in our case, what we can use for this problem is, as a neural network, what we might use as the base of our neural network. Assuming we want to do some transfer learning as opposed to learning this all from scratch. So what do we do for dog breeds? ResNet. So we could use ResNet or VGG or something that's already been pre-trained that knows about these categories and has lots of nice features and so on. And then we'll retrain retrain that basically. So you can imagine we just have a fully connected layer and then have an output layer. And if we want bounding box and category, then we're going to need to have basically 4 values for the bounding box and however many categories there are. Yeah. How will we represent the bounding box? I'm going to claim it's 4 numbers. I suppose you could over-specify and say you're going to specify each corner of the bounding box, but it's making your life harder, and it's certainly making the neural network's life harder. It's like not only do you have to get these numbers right of the bounding box, make sure these all add up too. So 4 numbers, 1 possibility. Okay, so we can have height and width. And here as well, as you say, we could do fractions, let's say, of the total image. Or alternatively, how could we represent it? Yeah, pixel values. So either of those are a possibility. What would we need in addition to height and width? Yeah, we need 1 coordinate. So it could be top left. It could be center. It could be bottom left. It could be bottom right. Any of those. We just need to decide what it is, right? And we can convert our ground truth into this format. Where will we be doing that? That is, where will we actually be using the ground truth? Given these 3 questions, which question is the ground truth coming in? Say again, Richard. Yeah, above the loss function. Exactly. That's the only place we're going to be looking at the ground truth in that loss function. So we'll just take whatever format the bounding box is and convert it either one time or every time in the loss function to the same format that we want our neural network to output. All right, by the way, one nice thing about this is when you scroll, the comments go with it, right, the writing, and I kind of like that. And you can go back to them if you want. So. All right, so this is, works pretty well. What would we use as a loss function? So if we want both dog and bounding box, what would our loss function look like? Okay, so we could use cross entropy for the classification. So cross entropy for the class is what we predicted, what we got coming in as the ground truth, and if that's all we have, it'll never learn bounding boxes, right? So we've got to make sure that we also add some. What would be the simplest thing we could use for loss for bounding box? For one of these values for the bounding box, let's say. Yeah? Okay, L2 normally, Euclidean distance, or even L1, the Manhattan distance, right? The difference, why do they call it Manhattan? Because if you've ever been to Manhattan, it's laid out in a nice grid of 90-degree square things. So the Manhattan distance basically says if you need to take a cab or walk on the street, how long does it take? So from here to here is a distance of 2, whereas, so the L1 distance equals 2, the L1 distance, sorry, the L2 distance, which is basically the crow fly, assuming crows can fly through buildings, is, yeah, square root of 2. So the L1 distance is strictly larger than the L2 distance. Okay. So we could use either one of those. We could choose some distance and use the bounding box coords where we both have the predicted and the ground truth. How would we know what this weighting factor should be? What's a way we could tell? mean, it is a hyperparameter, but how might you just come up with an initial value for this? Principal.
Can you use the other magnitudes that you expect? The other magnitude.
How do you know the magnitudes to expect? Will the cross entropy give us a number between 0 and 1? Right, because we got negative log of some fraction, so we could get large, which is good because we want our loss to be able to reflect both really big things and really small things. So I like the idea of comparing magnitudes, but I don't like the idea of prefiguring out what we think the magnitude will be. So what's another alternative? Speak louder. Oh, so the question is, how can we determine what weighting factor to use for the cross entropy, that is for the categorical loss, versus the bounding box loss? And the idea is, pick a constant so these are roughly the same magnitude, right? Assuming they're kind of important. And that is just what Principal said. But how do you figure out what the magnitudes are? Just try them. Just like run this and set a breakpoint or put a print statement in and say, oh, this loss is 1,000 and this loss is 20. I guess you need a factor of about 50. Okay? That's a good way to start. I'm not saying that's what your final value will be, but that's a good way to start. Does that make sense? Okay, so extremely empirical. Let me show you one more thing about this nice software. I can turn it over and the eraser works. Not true with my other software. So, okay, multiple objects. So we wanted to predict multiple categories. And the one change we made, well, we have to change the loss function, but we also have to change the architecture. The data is the same. We're going to just throw away bounding box information. What's the architecture change? Right? We did have for 4 numbers, which we had to figure out what we're going to use as our activation function for. Plus, we had 20 or however many categories there are in a softmax. So now, Evan?
Instead of the last layer being softmax, they're all in a sigmoid version?
Yes, so let's change the softmax for the categorical output to sigmoid. And actually, we don't care about the bounding box ones because we're not solving bounding box in this problem, right? We're tiptoeing our way to be able to do a full object detection, okay? And so this is another step closer. Okay, we'll have to change our loss function. Of course, we don't have anything to do with the bounding box there. And this should work. Category and bounding box of the largest object. This is fairly straightforward. So it is really the same architecture. So this is same as category and bounding box of a picture with a single object. So the one we had before that just had a dog. Because our output is the same, right? We are saying, I take it back. This is not the same because we have multiple categories. And in the previous case, we had one category. So sorry. This is multiple objects, but picking out one, the largest object. So let's just back up 20 seconds. So it's the same as the category and bounding box where we had a picture with a single object in it. So we'll have 20 categorical softmaxes and 4 ReLUs maybe, or maybe we want to use sigmoid because we want a number between, if we want a number between 0 and 1, which is the fraction of the total image, then sigmoid's a good choice. If we want a number between 0 and let's say 224 because that's the image size, What's a good way to get a number between 0 and 224? What's that? Yeah, we could scale the sigmoid. So we could either have a custom activation function with a scaled sigmoid, or we could move the scaling to where? We'd have to move it to the loss function, and then we'd also have to move it somewhere else too, and that is to the prediction, right? When we're doing predicting, we need to make, if we want numbers between 0 and 224, and we have them between 0 and 1, then we need to convert it to 0 and 224. All right. So this will also work as well. And the key thing I want you to keep in mind here is there's no problem in figuring out which object is being predicted and which the ground truth object that corresponds to that. Because we take the ground truth and we just take the largest area. And that's easy enough to do. If we could do a tiebreaker if we need to, but it's very easy to say, this picture, it's the dog. And we know what we're trying to do is train this neural network so that this output says dog in here. And this is not going to be the case when we get to multiple objects. And that's really the trick of multiple objects, is figuring out how to correspond the objects in the ground truth, the picture, with what your neural network is outputting.
Are we leveraging Pascal's, like, do the Pascal images come with the labels and the bounding?
The Pascal come with the labels and bounding boxes.
And they're leveraging that to the
Yeah.
prediction.
Yep, exactly. They actually, I believe the Pascal also includes pixel boundaries here. At least one version of it does. And we'll maybe touch on that at the end of class. All right. Here we go, multiple classes. Multiple classes with bounding boxes. Here's the issue. What we have here is ground truth. All right? Let's say that our output for our neural network, and I'm representing this pictorially because it's easier than writing down a bunch of numbers, right? Let's say it has dog and cat. Okay? So it spits out, in fact, we haven't even figured out how it's spitting this out, so maybe we need to even talk about that. How is it spitting out both this and this? That's a function of, right? Which of these three questions addresses what's our output of our neural network? It's the architecture. So how do we get it to output this? What is coming out of our neural net? What's the final layer look like?
Five times the number of categories.
5 times the number of categories. Okay, and the 5 comes from?
4 comes from the degrees of freedom we have for rectangle, bounding box, and the fifth one comes from the classification.
So we have 5 times the number of categories. I'm trying to understand that. So in this particular case, we've got 2 objects that we are specifying. So we know at the very least we need to have, right, categories, not cats, okay, and a bounding box. And we need another set of categories and a bounding box. Do you agree? I mean, in order to get the data out, we need 2 bounding boxes, and we need 2 sets of categories, and we need them to be matched up with one another, right? We need to know which category goes with which box, so we just put them like this. Could we set up an output layer for this? No problem, right? Just some extra. We're duplicating the output. So this is great if we have two categories, or two objects, but we know the neural network is stupid, and it said there are only two, and we know that there are four. So we know because of the ground truth that really this neural network should be outputting more stuff, right? How many more things? Two more, right? So we really want to have at least this for this picture. But we don't get to design our architecture per picture, right? We need our architecture to work for all of our images. So how many do we need to possibly be outputting? The number of categories in Pascal might not be enough. Remember this picture. How many categories is this in here, represented in this? But really, we have, a bunch of objects. So this particular image, we would want to have 6 different combinations of categories and bounding boxes.
You want as many as the largest number of objects in your data set plus some extra amount so that you're in your own network.
Yeah, as many as you'll need in your training set, plus more because maybe you'll see more in your in production, right? So we may have a lot of these. Let's look at question even number 1. So we've got some categories here with a softmax, right? So our sum of our probabilities equals what? 1. Our sum of our probabilities here equals 1. That's great. This one is saying dog, right? And this one is saying cat. However, what's the sum of these probabilities? 1. And the sum of these probabilities? 1. And yet, somehow, the neural network wants to tell us that nothing here. I have 2 objects I'm interested, that I'm telling you about. So how can the neural network provide us the information that I'm predicting a cat and a dog and nothing else? Does the problem make sense? Okay. So I can think of at least 2 ways. Go ahead, Principal.
Add an extra neuron that tells us the number of tens that
We could do that. So we could add a new neuron that says how many, right? And it'll tell us of this k possible outputs, how many do we care about starting from the top? And we could do 2. The problem is that's hard. And it's hard because it's got to integrate this information across all of these. And that will be difficult to train. Another possibility. Yeah. Put a little bit, a check mark for each one. But we're going to make it a probabilistic check mark. So the check mark says, yep, there's an object here. So there's an object here, and there's an object here, and there are not objects here. So this is the probability that there's an object. And so we'd be close to 1 for those top 2 and close to 0 for these bottom 2. Does that make sense? That turns out to be easier because these are independent of each other. Whatever part of the network that's worrying about this particular slot can decide for itself whether there's an object there or not. And this one can decide, and this one can decide, and this one can decide, and so on. All right. This isn't the hard problem. Let's get to the hard problem now. We've got a loss function. We know now what our neural network is predicting. It's predicting a cat and a dog, and we know where. We've got our ground truth that tells us, actually, there are 2 dogs and 2 cats. And now we need to determine our loss. And part of the way we're determining our loss is telling it, guiding it, kind of what to do better, in some sense. What do we tell it that we want to do better for this dog? Evan? Yeah, we could say, I think, fairly realistically, that this dog is this dog's face, right? It's missing out on its whole body. And so what would we say as far as the category, as far as the loss? Low or high? Categorical. Low. And bounding box loss? High-ish, right? Part of it's fairly good, part of it's not. All right, I'm with you there. Now we got this cat. Tell me about this cat. And tell me about which ground truth object we should be comparing it against. I carefully tried to make it ambiguous, right? So maybe its bounding box is pretty good, and it got the category wrong. Or maybe the category is just fine, but it's this cat or this cat, and its bounding box is off. And so this problem is, how do we match the outputs from the neural network with the ground truth object so that we can correctly match the loss? Because if we know our ground truth object and we know our predicted output, we know how to compute the loss for that. And we'll just sum them all up. But we need to have the right one. And not only do we have to have the right one, we want one where we're not changing all the time, right? Where one time through, we say, these are how they match. And the next time through, the matching happens totally differently because the neural network will never learn. So we need some consistent mapping. Here's what I want you to do. Break into groups of everyone at your table. So that's 3 or 4 people. And I want you to think of how, or brainstorm, so come up with as many ideas you can, of how to match these k items to, I mean, let's just say 4 right now, but however many ground truth items there are. Before I do, does a problem make sense? Because it's not going to help until the problem makes sense. Any questions about that? Yeah, Drew?
Just reiterate
Yeah, so.
the problem, because I think there were a few moving parts here with the,
Yep.
3
So-
boxes
so-
for each idea.
We have, let's assume we're going to use this format. So we have K, bounding box, category, probability that there's an object there. So we have K of these outputs, okay, in a particular order, right? So they're an ordered sequence of those. And our job is to figure out, for each bounding box, which ground truth object should it be comparing against, if any. And we want that in some way that will be consistent over time as these outputs slightly change, as the bounding box slightly change, or it changes the idea of the category, that we're not completely saying these k used to go to these objects, and now the next time through they're going to completely different objects. Right? Because if these get mapped to different ground truth objects over time, then we're going to run into a problem with learning, because it won't be able to learn if that keeps changing. Yeah.
So follow-up question. So the K, that's the largest number of objects in an image plus 1, and the categories that you have got to determine before take priority, like what those categories are.
It was part of it was what the labels were.
Okay.
So let me actually, before we go on this, let me give you one, and let's just analyze why it's a problem. Okay. So the one is, let's see. All right. Let's say we use, we'll order the predictions by bounding box area. And we'll order the ground truth by bounding box area. Does it give us a way to do the mapping? Yeah, so we take the largest bounding box we're predicting, the largest bounding box we want to predict, we assign that to it. Okay. The problem is that as our predictions are going to change over time, right? We're going to get better and better. So our bounding boxes are going to change size. Sometimes in the direction we want, and sometimes perhaps not in that direction, right? So sometimes we would like the bounding boxes to get larger, and they're actually getting smaller, or vice versa, for various reasons. Mini-batch differences, or we're overshooting our gradient, or other things like that. Okay. So what can happen is, I'm still using those 4 cat, dog, cat, or dog, cat examples. So let's say we have a big box, and a smaller box, and an even smaller box, and a really small box, okay? And our predictions are dog, cat, cat. If we remember, superimposing in our mind the picture, right? We had a dog and a cat and a dog and a cat, and these aren't so far off, although this dog is not, this bounding box is not very good. But what would we map these to? We would map this dog to this dog, which is great. And then we'd map, this is the second largest one, we'd map this cat to the other dog, right, this dog. And we'd map this cat to one of these cats, I don't remember whichever one's bigger, and we map this dog to the remaining cat. If, on the other hand, this dog square bounding box increased enough that it were second best, then all of a sudden this dog would, what we think of as correctly, map to here. But it would also change these mappings, right, of things that don't have anything to do with it. So making one change to a bounding box, it's because it's basically ordered. And so if you make one change and move it, everyone's location there and later in the list changes. Does that problem make sense? Okay, so here, I want you to spend 5 minutes and come up with the things you're going to come up with might run into the same problem. Just think to yourself, would it have the same problem? Because we want to try and exhaust possibilities. Go ahead. And afterwards, I will ask you to give me some possibilities. So.
Bound on how many classes we can expect from a single image. You said everything we're seeing in the training and then like some more.
Yeah.
But like typically I would imagine if we're doing a neural network that our data set would be like big, like maybe like the tens of thousands, not the hundreds of thousands. But
yes.
Wouldn't it be easier, like wouldn't it be better to get a lower bound, which is basically like the resolution of the image? So it's like a 200 by 200. That's like
yes.
4,000, right?
Okay, so 4,000 would seem like it's an upper bound. Yes.
Yeah, but and it's way better than like the 10,000, because you've seen like 10,000 or like.
No. I did not explain it well then. We take every image and we say, what's the max number of objects in that image? So it's the max across all images. So.
But that would not necessarily work. You could see more.
That's why we add some more to the. We add enough so we're okay, but probably less than 4,000. Sorry, and it's not 4,000, it's 40,000, right? Yeah, that's a lot. Feel free if you want to pull your chairs around so you're actually next to each other. A bad option is better than no option at all. I like it.
Or I guess you can go like divide the picture into like different sections.
Yeah. Maybe one thing that would work is like in changing the example set order, the outputs and the like ground truth. You just order the ground truth and then like, you label the specific output. So this output has to
You just like say, oh, this one was a cat. You have to start moving it. It's still busy.
What did you say?
Like if you only have 3, then let's just come up with 3 bounding boxes.
We'll give it 2 more minutes.
What one is with the match everything up here?
There's two things like vertically and then obviously like just let it left and right. It sounds like here.
I feel like the one that overlaps the most would be that one.
In his example, I mean, you could have a big cat, right? Or you can have a cat right here. This could be a cat. So here, that's
Because you just maximize the one for like
Very like the objective box is
Whoop, not what I anticipated. Sorry.
that kind of makes it kind of
That's like, is there a
What if actually what the hats are here?
All right, so here's what I want to do. Let's go around group by group. We're going to do this in a brainstorm fashion. So I'm not going to judge any of these yet. So we'll write them down, and then once we've written them down and kind of have run out of them, then we'll go through and look at them and talk about them. Okay? So give me one.
just like left to right? Which one's first? Like left to right, left to down.
All right, so left to right, top to bottom. So the first one in scan order, the second one in scan order, the one in scan. So that definitely will match. And we have, this, of course, the same problem. Sorry, I'm not evaluating this. I understand. I've written it down. Go on.
so like kind of the same thing we did with area, but like instead of ordering both the alpha neurons and the objects, like only order the objects, and then the neurons are given specific like names, so that like one of them has to find the largest object, one of them has to find the second largest object, and so then it means that like
Oh, interesting. Okay, so we have neurons. Let me see if I see. So one of the neurons, let's say the first one, is responsible for the largest object, and the next one is responsible for the second largest object, and so on. Is that right?
yeah, and so then each neuron has to map onto like exactly one of the objects.
Okay, so neurons have specific jobs with respect to size. Largest, second, etc. Is that correct? Okay, you guys.
One of the ones we have is you put them into categories and then sort the categories from left to right.
Okay, so we're first sort of sorting by category, and then left to right within the category?
Yes.
Okay.
was thinking we could consider the intersection of the ground truth
With the prediction? So large intersection would mean?
Like, I guess we have to consider like so it's like if your ground truth is embedded inside your predicting box, then you consider that to be like.
That's the one, that's the match. If they intersect or intersect a lot, then that's the match. Okay. All right, I get the general idea. We have some details that we need to work out, but we're not evaluating. Go ahead. Did you guys not elect a spokesperson? Or did you not elect what would be spoken about?
Both.
I see. All right.
The last one? Okay, so, Carrie, correct me if I'm wrong. I think there was an idea that you can do something kind of similar to what the last people were saying, but instead of like just, if it didn't intersect with anything, just like permanently just throw out the neurons.
Is that, yeah, I feel like this, if like it doesn't match like anything, or it doesn't intersect and the ground truth running box and like don't even count it.
And when you say don't count it, do you mean don't count it as part of our loss?
Yes.
Or it doesn't match anything?
When it doesn't match anything, it's like not detecting any objects, so we don't count it.
Okay.
It's not a loss.
And so if it doesn't match, don't count it. Okay, do we have some others? You guys don't have to come up with more than this, but if you got others. So you want the intersection divided by the union? Yeah. We can talk about that. Anyone else? Do you guys have another one worth talking about? Okay, so left to right, top to bottom. Now we can evaluate. Right now we're out of brainstorm mode. So left to right, top to bottom, it will likely have the same sort of problem in that as an object moves a little bit, that can change the ordering. And so changing one object's mapping changes other objects' mappings. And possibly a lot of them too. Not just like objects that are real close to it, but could be anywhere. Ordering objects by size, I'm not convinced is any different from what we talked about before, because if the neuron, I mean, the way of thinking about it is different, that the neurons have a specific job, and that the first one's job is to map to the largest, and the next, I take it back. Yes, this is different. So, so what we're saying then is neuron 1, or really that collection of neurons for object 1, object 1's neurons are supposed to find the largest object. That's their job. So this is, in fact, completely the same as the previous example where we were just trying to categorize in bounding box the largest object. And then we have another one that does second largest, another one that does third largest, and so on. The nice thing about that is there's never any question, as we're looking at a particular image and its ground truth, as to what neurons are responsible for it, right? What predictions are responsible. So that might very well work. Sort by category. Left to right within category may have some issues. So now that I'm thinking about it, it may be that the biggest problem about this, so the biggest problem to face is, in some sense, sorting both of them. Sorting the neurons means that we're not giving any particular neuron a particular job. And when I say neuron, I really mean the collection of outputs, right? That chunk. We want each chunk to kind of know what it's responsible for, knowing in the sense of that we're training it via the loss function, you know, and the backward propagation. So number 2 here has the advantage that we have this fixed job. Number 3, we still have the same problem of movement, Number 4, we again have the same problem of movement because as objects change size, these intersections may change. And that may change, you know, other items. I guess it's going to probably change less because if we've got objects on this side, we're only caring about the ground truth objects and those bounding boxes that intersect with them over here. And what we do over here isn't going to make any difference. So it's more localized and might work better. And we're going to come back to this idea of intersection over union, so which is a number between 0 and 1. And if we didn't intersect with anything, don't count it. So we already have this sort of problem. Let me back up a second. There are two things. We've got these k outputs, and they have little check marks to say whether I'm a real one or not, right? Whether I think there's something there or not. The ones that say I don't think there's anything there, for the most part, you're going to ignore, right? You're going to, they're fine if they say there's nothing there and there's actually nothing there. If you overpredict, if you predict a bounding box that doesn't map to any ground truth object, then it makes sense not to just don't count it, because you actually need to chide it, right? You need to say, bad bounding box, you shouldn't be there, we don't want you, I am assigning you a loss. Okay? That's the case where we might have, you know, we did really good at predicting dog, cat, and then we predicted a turtle up in the top left when there's white space. Okay? We're not going to punish it for saying turtle, because it had to say something, and it had some bounding box. We punish it for saying there's something there. Does that concept make sense? Okay. So here's an idea. Create cells and say, this is the first object output. This corresponds to this cell. And the second, and the third, and the fourth, and the fifth, and the sixth, and the seventh, and eighth, and ninth. And we just happen to have 9 right now. So our k is going to be equal to 9. Okay, this isn't going to be perfect, but we're going to work our way up to what we want. So each of these cells is making this prediction we just talked about. So it's predicting the probability that there is an object there or not. And then the classes, and then the bounding box. And we've got this repeated 9 times. In fact, let's look at another way to view this. We're going to probably use a CNN to do this, right? What if we had our output of our CNN be 3 by 3? 3 by 3 by what? How many features do we want at the output layer? 5. Where do we get 5? Oh, plus the bounding box? Okay, so yeah, so we would have let's say this would be our PC, right? And then here could be all our categories. And then here, our bounding box. So yeah, this is 4 big, this is 1 big, and each of these categories is 1 for every category. All right. So we could do this. We could also have our last layer just be flat and have fully connected to whatever's before that. Either one would work. This is kind of nice because we're keeping our spatial representation, and we're saying, and here's kind of what we're saying, is there an object that overlaps this cell or not? So for instance, for this cell, and we're going to have to talk about what overlap means, but we could say there's certainly a smaller probability for this blue cell than there is for the red cell, right? There's just a little bit of an ear there. And so it might be that this blue one is predicting no object. And then the red one, we would want to predict yes object. And it's a dog. And it needs a bounding box. So we are not saying that these are cells or bounding boxes. We're just saying this is how we number our neurons and say what they're responsible for. Just like you guys numbered your neurons and said the first one's responsible for the largest, the second's responsible for the second largest. We're saying here, this one is responsible for an object that overlaps this, where we haven't quite described what overlapped means, but enough, overlaps it enough. And so's this one, and so's this one, and this one, both are probably responsible for the dog. This one thinks I overlap the dog a lot, I need to predict the dog, so does this one. This one, probably not. This one, it's either going for cat or for dog, I'm not sure which. We're going to have to figure that out. It can't do both. This one, we're going to have to figure that out, the one out too. This one might be responsible for the cat, and this one responsible for the cat. So ideally, we would have this cell say what? Is there an object there? I'm going to say no, not very much of one. Let's say we want it to intersect with this cell a fair amount. A third, maybe. So nothing intersects a third here, nothing intersects a third here. We're going to say there's nothing there. That's what we want our neural network to do. Here, we want it to say, what's the category? Dog. Is there something there? Yes. And what's its bounding box? Is it this red? No. It's the entire dog. Unfortunately, this one's going to say the same thing. It's unfortunate. It's not so bad, two things saying the same thing. We'll have to deal with that. This and this probably will say cat, and both have the same bounding box. And this becomes a little less clear. This is probably yes, and it's a dog. And one of these is going to, they're either going to be cat or dog, and I don't know which. And do you see how we're independent of one another? Each cell just worries about its thing. What object am I overlapping? And what's its category? What's its bounding box? What object am I overlapping, if any? And what's its category? What's its bounding box? All right. These cells, are they part of the input? Are they defined anywhere in the input? No, not in the input. Are they in the architecture? Kind of they are, because we got 3 by 3 there and we got a 3 by 3 there. So yes, and the receptive fields will sort of correspond, right? This will be more at the top left and this will be more at the bottom right. But we could have done this as just a flat layer. And if it was a flat layer, the architecture wouldn't know anything about it, other than there were 9, right? That it would know that there are 9 possible objects. It's the loss function that really knows about these cells. So the loss function knows about the cells and does calculations for the cells, right? Like the neural network tried to figure out, is there an object overlapping this cell? In our loss function, we're going to kind of have to do the same thing. Is there an object by looking at the ground truth, is there an object overlapping this cell? If so, I know what its class is, I know what its bounding box is, and I know where in my neural network output to find the thing that should be predicting that, and I can now go do a loss. The reason I spent so much time before this in trying to show the matching problem and how many ways there are to get the matching problem wrong is because I don't find this approach just springs to mind very easily, right? It's not the first thing you'd think of. And especially later on, we're going to talk about more boxes than this. So more than there's just this 9 by 9. We're going to add a lot more, but we're going to use the same sort of idea. So questions right now? Yeah?
So like, is the size of the bounding box like a hyperparameter, or is
the size of the bounding box, like what size this is going to say that their dog is.
Or not the bounding, or sorry, not the bounding box. I mean like the
cell size. Yeah, the cell size is. Yeah, we could consider that a hyperparameter. How many cells you have? Yeah, definitely. So, matching to ground truth. So our ground truth is shown here, and now we want to look at, yeah, Laura.
I'm sorry, I'm just confused because I thought the number of cells affected what your output was, so I'm confused how that would be a hyperparameter if it's embedded in your architecture like that.
Well, number of layers in a neural network is a hyperparameter as well. So your architecture, in some sense, some of those things can be a hyperparameter. All right, so let's say we've got this bounding box, and it says cat. Okay? Which cell is producing that? I don't know. We better go find out what cell it is, right? We need to go look it up. If it's cell number 4, we're happy. If it's cell number 9 that's predicting that, no, not good, right? You're not responsible for this. So if cell 4 or cell 7 is saying this, good. Does that concept make sense? Right? We do know where it comes from. So we're not just saying we have 9 boxes and 9 categories. We have 9 in a particular order, and we know how they map to the cell. So what we're going to do is we're going to look at intersection over union. So let's look here at, so the idea is we take the intersection, let's just ignore that a second. And I'm going to erase this red thing, because what we're interested in right now is intersection with respect to cells. Later on, there will be some discussion we have of intersections of bounding boxes. But right now, let's say we're looking at this cell. And we want to know what object, if any, does it overlap with. We can look and see it doesn't overlap with the green, right? The cat. And I'm just ignoring these two right now, just focusing on these, the leftmost cat and the rightmost dog. They're these two. The intersection of this is 0. So there's no overlap. Done. The intersection of the dog, right, is here. And the intersection and the union is whoops. Okay, I'm still getting used to this. Is that right? So the intersection over union is basically a fraction of the red over the blue. So if we had a 1, we're perfectly aligned. If we have a 0, there's no overlap. And it gives us some idea of how much overlap that is. This is sometimes also called the Jacquard index. Okay. So what we'll say is, and we have a number here, this number is a hyperparameter, cells that have a high intersection over union, a high Jacquard index, with respect to the ground truth, are responsible for that object. Yeah.
What happens if, for example, in this case, we have just one very large, say, turtle, and then none of in the ground truth, none of the IOUs?
So that's a great question. Let's say you have a giant turtle. None of these is going to have much overlap, given our description here, right? Because it's a giant turtle. So we are going to extend this concept of cells to have different size cells. Big cells to capture big things and small cells to capture small things. And we're going to even have different aspect ratios to get tall and skinny things and wide and squat things. Okay. but it's too complicated to do to begin with. So we're just starting with this. Okay, but great question. So we want to match to ground truth. Here's what we're going to do. We're going to go through each cell, and we're going to find the ground truth object with the highest IOU. Are we looking at the prediction for this? Do we need to know what the prediction is in order to find this IOU? No, because I didn't say anything about the bounding box of the prediction. I'm saying ground truth bounding box, right? So this is the ground truth object bounding box with respect to cell bounding box, where cell bounding box is a constant. I mean, we know what it is, right, for any given cell. If the IOU is less than 45, we need to figure out loss. So we found, what does this mean? We have a cell, and its IOU is less than 0.45. Give me an example of a cell there that has that property. Top left. This is IOU less than 0.45. And I'm going to claim this one is 2. And I don't want to look at these yet. Our bounding boxes aren't very good for those 2 middle objects. So what do we want in the top left and the top right corner? What do we want as a prediction? No object. Do we care about the category? The class? No. Do we care about the bounding box? No. So are those going to be enter into our loss function? No. So we are going to just say we want to do, let's say, cross entropy with the ground truth. Sorry. We know what the ground truth is. There's nothing there, right? So 0 and the cell's probability of some object being there. Maybe this loss will be 0, right? Maybe this is already predicting, no, there's nothing there, and in which case we're great. Maybe it's predicting a giant turtle in the top left, in which case we have to tell it, no, no, no. I don't care about turtle, I don't care about large, but no, nothing there. Okay. Makes sense. All right. If we do have a high IOU, then that means we found some ground truth object for this cell. How can it go wrong? The ground truth object compared to the cell. What can be wrong? What's the high order bit that we care about? Whether or not it's an object. And is it an object? Yeah, so we wanted to say it's an object. So the first thing we want to do is do a cross entropy with the cells PC. And what are we comparing it against? 1. Okay. Plus some alpha, because we need to make these all kind of match up. How else could we go wrong? So we incorrectly predicted whether or not there was an object or not. Second, category. So we'll do, let's say, cross entropy on ground truths class. I'm putting really classes, right, because it's all of them, along with the cells classes. And when I say the cells classes, what I really mean, if we're talking about this cell, is the 9th output we had, or in the case where it was convolutional, the bottom right one. That slice. Plus some beta times what? Yeah, L1 or L2 loss of the ground truth bounding box and the cells bounding box. And this sucker will learn. Okay? It'll at least learn the things that have some overlap. Some of these objects that don't have a 0.45 overlap, right? It won't learn a giant turtle. It's probably not going to learn these two things, but it'll learn those. And there are lots of other images it might learn. Monday, we'll finish this up. And just as a preview, we're going to have multiple bounding boxes coming out for a particular object, right? Not just one. So we're going to have to fix that. Have a good weekend. And there's no assignment this week. We'll have an assignment next week.